Okay.
Okay.
Okay. And then we have the components that are the chemical constituents of the system. And in our case, in our rocks, most of the time we have measure elements like I introduced yesterday and trace elements. So the measure elements we introduced yesterday, we know what they are. So before in magma, as we said yesterday, is a complex material, is a multi-phase material with a liquid, with a melt, a silicate melt, exhaled gas, vapor bubbles, and different kind of minerals. The equilibrium of and where these phases can be formed is basically controlled by pressure, temperature, water content, oxygen fluidity, and we are going to see how these variables will affect at equilibrium conditions, particularly crystallization. So I'm going to start here with a very simple one-component system that is an aluminium Al2Se5. So basically, is we have three phases with this component system. We have kyanite, selenite, and andesite. Here, just introduce this just to make clear that we're going to talk about this kind of diagram with pressure and temperature. And I don't know if you are familiar with the phase rule, so with the degree of freedom of variance within this pressure and temperature space. The C of this equation is the number of components that in our case is 1 because it's a very simple system. R is describe the number of environmental variables in the system. So here we consider just pressure and temperature, so therefore 2. And then F represents basically the number of phases that in our case there are 3. So therefore at the point A here, so basically this point is invariant because at the end, if you do the calculation for the variance, we have one component, 2 phases, so 2 variables, 3 phases, and at the end we have 0. So basically we have a triple junction between andesite, sillimanite, and kyanite. If we consider, for instance, B is univariant, basically we can move just along this liquidus here. So in this case we have sillimanite, in another case we have kyanite, and if you do the calculation, basically the variance will be 1. Instead, if you move to the C point here, so basically here we can move in all this space. So therefore the variance will be 2 because kyanite will be stable if we increase the pressure or if we increase the temperature in this space here. So another diagram consider just one component that in this case is CO2, considering pressure and temperature as well. Here we see different type of quartz from tridymite, cristobalite that is low pressure, high temperature, to increasing basically towards coesite or schistosite, increasing pressure. Here is also introduced the concept of liquid very high temperature. So therefore it will be a one component with the mineral phases plus a liquid. So this is a very simple phase diagram just to introduce the concept of it. But we move basically towards a two-component system where a melt is involved. And I'll introduce the first case that are binary system. So 2 phases with an eutectic point. Binary phases, binary system with a peritectic point. And then I'll introduce a binary system with the thermal barrier. Then a binary system with with solids that have a complete solid solution, like plagioclase, and then a binary system where we have a partial solid solution, like alkali feldspar. After that, I'll move towards ternary diagrams that are closer to a magma, and then I'll introduce a phase diagram under water saturated condition and under water under saturated conditions that represent they represent magmas, real magmas. So here. Yes, the other things that I'll introduce is I'm going to talk about equilibrium crystallization first. So this one. And then I'll make the difference between equilibrium crystallization and fractional crystallization as processes that control magma differentiation. And then I'll introduce also equilibrium melting and fractional melting. This is just the reverse process, starting from a crystallized magma moving to a liquid. So here is very simple system with two components involving melt, and here we have water plus a certain amount of NaCl, basically salt, versus temperature. And here you can see the liquidus, the evolution of the liquidus, where in this case you have liquid, so water, and here you have basically crystallized in your ice. Basically. You have crystals. So if we move towards magma, it's a little bit more complicated, but not too much. In this case, it's not really a representative of magma, but it can be close to it. In this case, we have just a solid solution between anorthite and diopside, where basically here we have the 8% of anorthite, here we have 100% of plagioclase, and here we are going towards 100% of diopside. Okay. And we have temperature here. These two lines represents liquidus. So here everything is liquid. And in this field, basically we have diopside plus melt. In this field, we have anorthite plus melt. Okay, this field here. And this line represents basically the solidus. So under temperature lower than this line, everything should be crystallized 100%. Okay, we have this point that is called the eutectic point that represents the lowest temperature at which the melt may be present. Okay. Oh, if we do the reverse, if we increase the temperature, lower temperature than 1280 degrees Celsius, so if we start from here and we increase the temperature, it will be the first melt produced from a crystallized rock, from a fully crystallized rock. So therefore, the eutectic point is the lowest temperature at which the system, the melt will survive. After that, everything will be fully crystallized at equilibrium conditions. So this, just to be clear, this is valid at equilibrium conditions, because of course, if I move quickly my temperature and not giving time to the system to re-equilibrate, I can have a completely glass at this point here. So I can produce glass, what is happening in volcanic rocks like obsidian and so on. So therefore, what we are discussing here is just crystallization at equilibrium condition. So this is the same diagram, just an example. Here we move from this liquid M to this point here. And so what we have is, at this point, everything is liquid. We decrease the temperature, And when we meet this liquidus here, we can produce the first anorthite crystals, okay? And decreasing the temperature, the amount of anorthite will increase, okay? Because we are going far away from the liquidus, okay? And when we reach basically this point, so the solidus, here you will have the evolution of the liquid that will be depleted in anorthite up to the eutectic point, and the eutectic point the dioxide will be formed. Okay, and so below this temperature, around 1274, basically we have a completely crystallized rock with dioxide and anorthite and plagiates. Okay, if we do the reverse, so this is equilibrium melting. We start from an intrusive rock with the dioxide and anorthite. Okay, it can be like a gabbro, for instance. So if we increase the temperature, when we reach 1274 degrees Celsius, so dioxide will start to melt. Basically, we form the first liquid, and then the liquid will evolve, increasing the amount of increasing temperature. So the amount of anorthite will increase, because then the plagioclase will be dissolved as well, increasing the temperature here, up to reach the liquidus, where basically the last crystals of anorthite will be dissolved. And then when we reach the end point, our rock will be completely liquid, so we will have a liquid. Okay. Now I want to introduce a binary system with a peritectic point. So we said, okay, this is the same basically. We have, in this case, we have a forsterite, estatite, and quartz. It's more clear here. Yes, is a forsterite, estatite, and quartz. Okay, and we have the eutectic point here. So this is the same point that we discussed before. Is the lower temperature where the liquid survive. And then here we have, though, since we have three phases, we have this liquidus, that is the forsterite liquidus. Then we have where in this field we will have forsterite plus melt. Then we have another liquidus that is the enstatite liquidus here, where in this field we will have enstatite plus melt. Here everything is liquid at these conditions. And then we have this liquidus here, that is the liquidus of quartz, the quartz liquidus. Okay. And then we have two solidus. One here that is valid for the forsterite, and one here that is valid for the enstatite quartz. Okay. And now depends where we start. Depends, the equilibrium crystallization will depend on the composition of our liquid. So if we have a composition, for instance, here, I don't know if you see here, okay. So if we decrease the temperature, okay, I don't know if it's clear from here. No, it's particular. We can do here. So this is the same diagram. If we have, we start from a composition here, okay, we decrease the temperature, so the crystallization will follow the same path that we said before. So from here, touching the liquidus, forsterite will be formed. the amount of phosphorite will decrease in temperature, because we will be far away from the liquidus, so the crystal volume fraction will increase up to reach this point here, that is called paritative point, where in this case, since the composition is completely within this field here between the phosphorite and enstatite, at this point will be representative of like an eutectic point, where basically the liquid, the last drop of liquid will form enstatite, and then we go in this field, basically. Starting from this liquid, at the end we will have an intrusive rock with phosphorite and enstatite, because this point will work like an eutectic point. But if we shift a little bit our composition, and our composition will be within this field here, so even if it's touching this phosphorite liquid, okay, when we decrease the temperature, we will enter in the subliquidus of the phosphorite. Phosphorite will be formed, but then when we reach the paritative point here, this point here, the paritative point is a reaction point where basically the phosphorite will be dissolved, and the system will go ahead in this way, going to the eutectic point between enstatite and quartz. So therefore, at the paritative point, phosphorite will be dissolved and enstatite will be formed, okay, up to reach the eutectic point where quartz will be formed. At the end, starting from this liquid at equilibrium condition, we will have enstatite plus quartz and no phosphorite. So an example of this can be intolitic basaltic magmas. You see often, particularly in rocks like the ocean ridge basalt and these kind of things, where you have a reaction. The olivine is showing a reaction, is dissolved, partially dissolved, and you have like a corona of pyroxene around it. So that is representative of the paritative point, just that the system didn't reach the equilibrium, the olivine didn't dissolve completely, and you have just the overgrowth of pyroxene around it. Is just this paritative point that is moving towards. So the proper eutectic point. Okay. And here is just describe what is happening with this, following this point, this path, basically. You have a phosphorite plus liquid in equilibrium here, then phosphorite liquid will react and we form enstatite at the paritative point, and then you go towards the eutectic point where you will have enstatite plus, in this case, crystal balance. Okay, so this is representative of equilibrium crystallization, what I said before. If we move instead to fractional crystallization, the story is different, because even if we start from the initial point that is the OTH, the first example that I explained, where we are within the field of phosphorite and enstatite, even if we start from here, since fractional crystallization means that we remove physically crystals from the liquid, so basically this paritative point will not work like an eutectic point, as I said, for the equilibrium crystallization, but actually is a paritative point. The system will shift towards an eutectic point, because what is happening, the fractional crystallization, the assumption is that you remove physical crystals, and the liquid will be able to reach basically the eutectic point that is here. So, okay. And the same story is for fractional melting, just is the reverse. You fractionate liquid up to you reach that point, the final point. Okay. Now, what I'm going to introduce is a binary system with thermal barrier. Okay. This is a thermal barrier that is not present in this fosterite-estatite quartz diagram. At basically, this is a representative of ambient pressure or low pressure. Okay. We don't have any thermal barrier, but we have a peritatic point and a tectic point. But if we increase the temperature, if we increase the pressure up to this example was made at 1.2 gigapascal, we have basically a thermal barrier where or we are in this field or we are in this field. So basically, we have two rotative points, one between estatite and quartz. The other one is between fosterite and estatite here. But actually, we don't have a peritatic point anymore, and we have a thermal barrier. So it means that if we have a liquid that has this composition here, we'll go to this rotative point, and we will have fosterite plus estatite. If we have a liquid that is here, we will go towards quartz. So in some way, this can explain why, at the end, in basaltic rocks, it's difficult to have quartz and olivine together because there is, at the end, like a barrier. Also, if you remember the tetrahedron of basalt, now you have a different barrier where it's difficult to move from an olivine basalt to quartz toluene. Okay, the same here, and then I'll try to make more simple. This is still another binary system with thermal barrier, but instead of olivine, we have nepheline. Nepheline is a phosphatoid. Okay, so therefore we have the nepheline plagioclase quartz. Okay, and still we have this thermal barrier, or we are in this field where we have at the end the rotative point where nepheline and albite will be formed, or we are in this field where plagioclase and quartz will be formed. This is quite representative if you think about okay, this is exactly the same, so it means what I said before. If we have a liquid here, we will finish here. If we have a liquid here, we will go here. Okay, there will no cross, basically. So this is representative of this. Maybe you are more familiar with this, with the QAPF. So this classification of rocks for plutonic rocks or for volcanic rocks. So this thermal barrier is here. So or we are in this field between plagioclase and quartz, or between plagioclase and nepheline. But actually, if the crystallization will evolve, will push the melt to evolve towards this direction, usually. So what I'm saying is that if this is the task, if we start from here, crystallization will push your melt to go in this direction. It's difficult that you go from here to here. Okay, so this barrier is just showing that we cannot go from this composition when crystallization will occur. We will go in this direction towards rhyolite. It's difficult that we'll go here. If we go towards here, means that we have alkaline magmas, okay, like these ones, okay, and during the evolution, during crystallization, alkali feldspar should be formed, and then one alkali feldspar should be formed in more evolved liquids. So this can decrease the amount of silica in your melt, and so therefore it will push the liquid toward under saturation in silica, and this will form feldspar. So Leucite, nepheline, and so on. So therefore, this thermal barrier is showing that this why we have this division. It's not just a graphical division, it's thermodynamic. So there is thermodynamic reason why we have this. Okay. Okay. From a binary system with a thermal barrier, I'll move to a binary system with a solid solution. So far, we saw that we have all 100% of one phase or 100% of the other phase. So two phases can be formed at the same time, but there was no solid solution between the diopside and the plagioclase, or between plagioclase and pores, or between forsterite and estadite. In this case, in this diagram, instead we introduce the concept of solid solution within two phases. We have the anorthite here and the albite here. So here we have a 100% albite, here we have a 100% anorthite. Basically, it's a plagioclase mineral. And basically, here we have the solid solution between the two. So this diagram shows the liquidus of plagioclase. Everything above this liquidus is completely liquid. We have the subliquidus condition here, where plagioclase will be in equilibrium with melt. And then this is the solidus. Below the solidus, everything is crystallized, 100% crystallized at equilibrium condition. The same things we can. So we can introduce also olivine. It works in the same way, just at different temperature. The liquidus and solidus of olivine is at higher temperature than plagioclase, and we have a solid solution between forsterite and fayalite. So the forsterite is the magnesium olivine, and this is the iron one. So in this case, we have a calcium plagioclase and towards sodium plagioclase. So how does it work? This the crystallization here, how it works. So I'll introduce briefly how it works. Crystallization, equilibrium crystallization here, and then we go to see the effect of crystallization. So if we start from here, we decrease the temperature. So basically, at this point here, we start to form a plagioclase. Sorry, this is for olivine. We start to form an olivine with 60% forsterite, okay? And sorry, no. This is 25 more or less percent forsterite. This is the first crystal that can be formed. This is just the evolution of the liquid. This is the evolution of your fayalite, the composition of your fayalite. Okay, so therefore, first olivine will be here with this composition. The liquid will be this composition. So it means that going down up to the solidus, the liquid will evolve in this way. So it will be enriched in fayalite, and the crystal will be as well enriched in fayalite. So we go from 25% of fayalite up to 60% of fayalite. So therefore, the first crystal will be more forsteritic, and then we go more towards more fayalitic olivine. And here you can follow the evolution of the liquid in this diagram, where you have the percent of melt versus temperature. The point one is this, where we have basically 100% of melt close to it, and then the amount of melt will decrease because crystallization will occur at point 2 up to reaching the 4 point that is representative of the solidus, where everything will be crystallized. So therefore, 0% of melt, 100% of crystals. Is it clear? Okay. So considering this, we go, so we move towards the plagioclase system, but the concept is the same. So we make the difference between equilibrium crystallization and fractional crystallization. So at equilibrium crystallization, if we start from this melt here, we decrease the temperature. This is the ratio between melt and crystals. So 99% of melt, 1% of crystal. The crystal will have this amount of, this is anorthite, this albite will be more calcic, more anorthitic, okay, the core. And then if we decrease the temperature up to 50% liquid, 50% crystals, and we see the evolution of crystals at the equilibrium condition. So it means that there is equilibrium between the crystal and the liquid. At the end, what you have is the plagioclase will be more less calcic, a little bit more albitic, up to reach basically the solidus when so we have no more melt and we have 100% of plagioclase, where the composition of the plagioclase basically moved to 40% of anorthite and 60% of albite. So therefore, there will be an increase of of sodium from the beginning to the end. So at the end, the crystal will be more albitic than anorthitic. If we consider fractional crystallization, since we remove the liquid, so we remove the crystal from the melt, so that we don't have any more the equilibrium between the original melt and the crystals. At the end, what we can form is we can form this zonation. So starting from the initial core that is more anorthitic, we can end up in a more albitic rim just doing this. So fractional crystallization can register the evolution of the melt, and if you remove the crystal from the liquids, where you don't have more equilibrium between the two. So what you get is basically this.
So in the end, once you crystallize everything, the ending composition is that of the final melt, like the final solid composition.
Yeah, is here. Yeah, for sure. That what it means that also the amount of liquid that you will have will be enriched in sodium, and at the end, what you get is the last rim that you can form will be more albitic than the intermediate conditions. Okay, so therefore you will have the registration of each step every time that you remove the crystal. So this also is quite good as represented and good to understand how it works magma mixing, for instance. If you change the liquid of your because you
so fractional crystallization would be like a very fast change.
Yeah.
So that the crystals do not have time to re-equilibrate.
Exactly.
They just produce the ring.
Exactly.
Yeah.
Exactly. Or if you change the melt because you have a mixing, you will end up in this. So for that reason, often inverse or oscillatory zonation are related to magma mixing, because maybe you have more pools of different magmas, and you have.
Is there any model for calculating like differences in rates? For example, the time necessary for reaching equilibrium crystallization against the rates that involve magma mixing, for example, which can be sudden.
There is no, actually, nobody studied in a systematic way the effect of crystallization during mixing and vice versa. So therefore, people that study mixing at superheating conditions where crystallization was inhibited, or people that study crystallization just in a pure liquid without different. So therefore, actually, we don't know. So I performed some experiments, preliminary experiments that at the moment the data we produce a paper is under review where we investigated this gray area, and it depends on the condition. Crystallization can dominate over mixing or vice versa. It depends on the conditions. It's difficult to predict what is going to. But if the crystallization will dominate, you will see basically that the mixing will be inhibited, but you still see the evolution of the composition from the core to the rim. And we think that it's part related to equilibrium crystallization, so the evolution of the liquid close to your crystal due to crystallization, but maybe there is also effect of mixing that will evolve your melt, and so therefore you are going from more anorthitic plagiaries towards more albitic. But there are no systematic studies about it.
But you can also have just an increasing temperature without any mixing. And
yes.
So
yeah, absolutely. If you have basically a chamber that is with thermal gradients, so you can have just advection or convection within the magma chamber, going from a hot zone to a colder zone. So you can have this stuff. Yeah. But in this case, as Lucia said, you will have auxiliary, so you have inverse, normal. Yeah. Okay. This diagram represents the binary system in alkali feldspar. So before we move from plagioclase, where we have a complete solid solution, to alkali feldspar, where we have a partial solid solution. So, and the partial solid solution is due to, here we have albite and orthoclase. And this is the solvus, basically, where albite and orthoclase are not, they don't have the solid solution. And basically, this is the solidus. Okay, this is the rotative point, and this is the liquidus of the plagioclase. This is the liquidus of the plagioclase. This is the liquidus of alkali feldspar. This is the solidus. So basically, it works like the diagrams that I introduced before. Just what we have just a solid solution in this gray area here, and in this gray area here. Okay, but we don't have solid solution here. So this solvus and the solid solution depends on the pressure. So starting from very low ambient pressure condition to high pressure condition up to 500 megapascal, we see that the solidus is the temperature of the solidus will decrease up to around 650 degrees Celsius, where the solidus of the 2 feldspar is. So it means that if we have immiscibility, and when I talk about immiscibility gap, I talk about that there is really immiscibility between with potassium and sodium. So therefore, I have, in this case, I'll have based on, according to the temperature, I'll have microclean, orthoclase, cyanidine for the K feldspar, pure K feldspar phase. I'll have an orthoclase that is an alkali feldspar enriched in sodium, and then I'll have, of course, all the albite stuff on the other side. In this case, usually the miscibility, as I said, is temperature below 600, 700 degrees Celsius. What we observe in thin sections is this. This is representative of the immiscibility between sodium and potassium. So indicates certain conditions, for sure low pressure conditions. And then, yeah, just to put everything together. So this is the triangle of feldspar in general. This is the plagioclase where we have a solid solution at every temperature, every pressure, and then we have instead between albite and orthoclase this immiscibility gap at lower temperature than 700. At higher temperature, we will have this miscibility, and usually what we can form is an orthoclase that is typical minerals in alkaline magmas like trachyte, phonolites, these kind of magmas. Okay, and so what we have done. We have this immiscibility also in pyroxene. Okay, here we have the orthopyroxene, we have the clinopyroxene here, and we have ojite here, pigeonite here. Usually we have immiscibility in this field here. Okay, and also this immiscibility represents a certain pressure and temperature condition, and we have evidence in our minerals looking this kind of textures here where there is immiscibility between the more the calcium and the more aesthetic part of the pyroxene. And okay, so is everything we have questions? Okay, now I move towards ternary systems that probably are closer to magma. We have three phases, basically, and well, we have to see this ternary diagram like a connection of three binary diagrams. This is the binary diagrams that I introduced so far, with the solidus part, the solidus here, this here, everything below is completely crystallized. This the liquidus of one phase, this is the liquidus of the other phase. So therefore this field is the subliquidus condition where one mineral plus melt will be in equilibrium. This the other mineral plus melt will be in equilibrium. If we put three of those together, what we get is this diagram here. We have to look at the top of this, and basically the liquidus will be surfaces that will go towards a ternary eutectic point, so the lowest temperature where the liquid will survive. So everything after that, below that temperature, everything will be crystallized. And the liquidus surface is here. So okay, and these lines between two liquidus surfaces are called eutectic. Instead, the ternary point, the lowest point is the ternary eutectic. Okay, you can see here just so the three phases. This is the junction of this liquidus surface, and this one is ternary eutectic. The lowest point of the ternary eutectic are the ternary eutectic. Okay, and in this field, one mineral plus melt will be in equilibrium. Here, these lines represent temperature. So basically, we go from a higher temperature to a lower temperature going towards the eutectic point. Okay, just to make clear how it works, it's like this, and then basically these arrows represent basically the direction of the melt evolution. So basically, if we have like a point here, a melt here, so its evolution will be starting from this point. We will have like a line, okay, that will show the direction of the evolution, how we reach the cotected line, and then from the cotected line, the liquid will move towards the eutectic point, and then at the end, everything is completely crystallized. So if this is just an example, a simple example with 3 phases ABC, we have 3 eutectic point 1, 2, and 3 for the related to the binary diagram. We have 3 cotected lines that are this one, and then we have 1 eutectic, ternary eutectic point is this. The temperature will decrease from here to here, to here to here, from here to here, and the same here. So therefore the lowest temperature is the eutectic, and we move from the origin of the triangle along. If our melt, for instance, has this composition, we will move along this line. If our melt has this composition, we will move along this line. Okay, so and we track the evolution. So yeah, here is just to say that here we have 100% of this phase, 100% of this phase, 100% of this phase. So this point at the center will be representative of a percentage of the A phase, a certain percentage of the B phase, and so on. So, and if we go to here, just an example of the equilibrium crystallization. If we start from an endpoint here, okay, so basically we can follow the liquid path. The liquid path will be this one, this here, and then when we reach the cotectic, we will move towards the eutectic point, and then so therefore at this point here we will have just the B phase plus a melt. When we reach here the point 1, we will have B and A in equilibrium with a melt, and then our melt will evolve moving in this direction towards the eutectic point, where at this point we will have A, B, and C crystallized. Okay. Okay, it's exactly the same if we do the reverse in equilibrium point, and so equilibrium melting. If we have everything completely crystallized, the first point is this one, and then we will move towards here, and we will go back here. So for the first phase that will be dissolved is C, then A, and then we will end up with the equilibrium between B and melt. So just to, now we move towards a real magma that can be representative of a gabbro, or basalt. So where we have anorthite, diopside, and forsterite. Okay, if we have, for instance, this composition here, so this composition, we will have forsterite plus metal in equilibrium, and so if we decrease the temperature, we will go towards this cotectic here that is, we will have a forsterite and anorthite in equilibrium with a melt. Then decreasing the temperature, we will reach this eutectic point where the last phase that will be formed will be diopside. At the end, we will have basically forsterite, anorthite, and diopside together. So basically a gabbro. Okay. If we think about a fractional crystallization and we do the same path, so it means that if we have forsterite plus melt first and we separate forsterite, so forsterite will be able to sink into the into our chamber. So basically, and liquid will move towards then an anorthite, where the discotectic, where anorthite and forsterite will be in equilibrium, and then we separate these minerals, and then we move on, and we will form this point where we will have anorthite, diopside, and forsterite. At the end, if we think that this will happen, we will have like a dunite at the base as a first part of the crystallization. The liquid will evolve, and we will go towards a kind of basalt, a kind of gabbro that is like a trocholitic composition, and then we will end up to a gabbro composition here when everything is crystallized. So it depends if we think about equilibrium crystallization or fractional crystallization. So, and so just the last example here, we have this is a case where we have basically diopside here, even if it's covered, diopside, albite, anorthite. In this case, since we have a solid solution between the two, we don't have a cotectic between the two, because we have a solid solution. We have just a notetic point with between anorthite and diopside, and between albite and diopside. So therefore, we have just this cotectic here that it will go basically in this direction here, and so we have just all these rotative point, or this other rotative point there. In this case, so ternary diagram, as I said, they are quite representative of real magmas. But then if we want to reproduce, and we want to understand the equilibrium of several phases in real magmas, particularly under water saturated conditions, or under water undersaturated conditions, for instance, where water and CO2 are in the system, we can use these kind of diagrams that can be made through experiments. So we investigate every pressure and temperature condition in order to define the liquidus of our phases, and which phases are in equilibrium that melt, a fixed oxygen fugacity and water content. In this case, what I'm going to introduce is phase diagram of multi-phases magma under water saturated condition. This is a trachyplasmat of Etna, and the blue line is the plagioclase, and the red line is the pyroxene. This is the pressure and temperature. So it means that at this condition here, so above the red line, everything is liquid. Okay, we don't have any phase. So if we cross and we go in this field below the red line, so we will have a clinopyroxene plus melt in equilibrium. If we go a lower temperature, so here, below the blue line, this condition we will have a plagioclase and clinopyroxene plus melt at equilibrium. So the solidus probably, I didn't check which temperature will be here, so a very low temperature, where everything is completely crystallized. So this is an example for the trachyplasmat of Etna. And this slope is quite typical of clinopyroxene and plagioclase in magmas that are water saturated. Okay, they have this slope. This slope will change if the system is undersaturated in water. And we saw yesterday, the slope will change completely, and we go in this direction. A little bit like this. Here I reported, so therefore I'm going from basalt to rhyolite. Here I reported the phase diagram for basaltic andesite. This is a magma from Nicaragua, the Masaya system, volcanic system. And the dots that you see here are just experiments that you can constrain the conditions. So therefore, this liquidus here is the clinopyroxene, this liquidus here is the plagioclase, and this liquidus here is the oxide. So therefore, all the condition above these lines, basically, we can find just melt, it's just liquid, the system is just liquid. Then if we fix pressure like 100 megapascal, and we are here, at this condition, they found just clinopyroxene. For that reason, they put the liquidus here, and then the plagioclase is just below, because probably they find plagioclase and oxide here. And then if we go lower in pressure, like 25 megapascal, we see that if we move from here, where everything is liquid, to here, so the first phase that will be formed is plagioclase. This is quite typical of basaltic magmas and basaltic andesitic magmas. At lower pressure, there is the crossing of plagioclase and clinopyroxene. So it means that the clinopyroxene is representative of the bulk liquidus of the rock at higher pressure. But if we decrease the pressure, then plagioclase will be the liquidus bulk. Yeah. So, and then of course the oxide depends. The oxide liquidus is really sensitive to the oxygen fugacity. So therefore this can change depending on the oxygen fugacity. And also olivine is quite sensitive to the oxygen fugacity. Probably at more oxidizing conditions, oxide will be formed instead of olivine. Olivine can be stabilized at lower oxygen fugacity. So these experiments, I think, they were performed at nickel-nickel oxide buffer. If we decrease the buffer to QFN, it's possible that you will see also olivine, because they will be stable at more reduced conditions. So then I move towards andesite magmas. So here we have the experiments performed by Hammer and by shared Hammer, different magmas. And what we see that in this type of andesite, we have orthopyroxene, clinopyroxene, magnetite. Then we have a plagioclase here. With this crossing, a certain point, lower pressure will be the liquidus of the bulk. Instead, the higher pressure or pyroxene will be the liquidus of the bulk. And then the hornblende that has this typical slope. The liquidus is like that. So it means that it's stable here. Hornblende are stable at higher pressure under water saturated condition. If you decrease the pressure, so hornblende won't be stable anymore. So therefore, when you see these reaction rings of hornblende, means that they passed certain time lower pressure, so far from the equilibrium pressure and temperature conditions. So the same you can see here is slightly different, but still you have the clinopyrox. This is the oxide, olivine. Here you have olivine. Probably the two experiments were performed with two different andesite and probably two different oxygen fugacity. Here you have olivine, clinopyroxene. Orthopyroxene is just a lower pressure. The amphibole is here with this classic slope, and the plagioclase is here. Okay?
Oxides here are
this is magnetite, this is chromospinel. So also the composition can change depending on the oxygen fugacity of the composition. Dacite is not so far from andesite, just what you can observe that all the liquids are slightly shifted. They are similar to the andesite. Just the liquids are shifted at lower temperature. So if you see plagioclase, orthopyroxene, and chronopyroxene are between 950 and 1050 degrees Celsius. If you go to the dacite, all these liquids are shifted 100 degrees Celsius lower. So because basically increasing the amount of silica in the system, basically from andesite to dacite, the composition is not so different, so the equilibrium are not so different, but the minerals will be stable at lower temperature. And then well, you can see a very low pressure, low temperature quartz can be stabilized. Then we move to a rhyolitic magma. This is the Chaitén in Chile. Perform a nickel-nickel oxide +1. Still, water saturated condition, pressure and temperature. And you see that in this case you have plagioclase, orthopyroxene oxide, and instead of hornblende, you have biotite. Hornblende is no more stable here, but hornblende and biotite have this, the liquid has this slope that is completely different from the others. Still, biotite will be stable here, it won't be stable here or at lower pressure. Okay, so also biotite can dissolve quite quickly at lower pressure or at very high temperature. And still, you can observe that orthopyroxene and plagioclase are stable at lower temperature than dacite. Okay, we go towards 770 degrees Celsius at the same, a similar pressure. Yeah, for the dacite, plagioclase is stable from 900 or 880 maybe. If we go to rhyolite, will be stable at 770. For the andesite, is stable at 970. So basically, shift 100 degree moving from andesite to dacite, and other 100 degree moving from dacite to rhyolite. Okay, so therefore all the liquids are shifted at lower temperature. And then I reported the trachyte. So therefore we moved from calc-alkaline magmas towards alkaline magmas. This is trachyte. In this trachyte from Campi Flegrei in Italy, we have the magnetite here. That is the liquidus of the bulk composition. So it means that above the magnetite, everything is liquid. Then we have the biotite is here. Okay, we have chronopyroxene, and instead of plagioclase, alkali feldspar here is stable. Plagioclase in this composition is not really stable. You have to go towards less evolved trachyte or close to latite to have a plagioclase and alkali feldspar stable together. So, and usually plagioclase, when it's stable, it's a lower temperature than alkali feldspar. And here I reported also the solidus. So therefore you can see here, this is the solidus. Everything is crystallized below here. Between the solidus and the magnetite, we have all these subliquidus conditions with different phases that can be stable depending on the pressure and temperature. All of these liquidus are basically, they have these slopes because the water saturated condition. This is the last example. We have a phonolite from Vesuvio. We have a pyroxene oxide. In these phonolites, we have the equilibrium also between sanidine and plagioclase. And here you can see also, since these phonolites, they can go towards forming phosphatoids minerals. We have leucite. that under water saturated condition, the liquidus is like this. So it means that leucite can be formed a lower pressure than 150 megapascal. Usually is a phase that is stable a shallow pressure, and in a narrow range of temperature. So lower than 800 degrees Celsius, you don't form leucite in these phonolites. Higher temperature than 900 degrees Celsius, you don't form leucite in these phonolites. And then you have the classic amphibole that is here with the classic shape. So all of these are under water saturated conditions. Now I take the same phonolites. In this case, we have Pompeii with the same phonolites that the Pompeii eruption, so the Plinian eruption of the 79, so that destroyed Pompeii, the Plinian eruption. This is the phase diagram under water saturated condition. And if we move here, you have the same composition, but under water under saturated condition. So, and in this case, this is a phase diagram produced by the Orléans group, Bruno Scalier and Raffaello Scioni in Firenze. So here they mixed different amount of water with different amount of CO2. So without reaching the saturation. So therefore here we don't have more pressure, but the pressure is fixed. The oxygen fugacity is fixed, and then we have temperature and the range of water investigated for that pressure. And you see that yes, a little bit more complicated. So anyway, the liquidus of clinopyroxene is here. We have garnet. We have different pyroxene here. We have amphibole. We have nepheline. We have. It's quite tough to read. The solidus is here. Okay, and here is reported the amount of water that was dissolved into the melt. Okay. And here you can read basically as a function of pressure and versus the amount of water at fixed temperature. Okay, so therefore you see the FESPA, the amphibole is like this, the leucite is like this, the nepheline is like this, the clinopyroxene is this, and the solid is this. So these kind of diagrams are made when basically we have water and CO2. And there are two important components if we want to consider them. So what we need to do is we have to change the amount of water and CO2 in our capsule. So therefore we cannot change the pressure, we have to fix the pressure and perform experiments with different amount of volatiles inside of our capsule at fixed temperature as well. So, and then we can investigate temperature, pressure, and water content, basically.
So the CO2 is fixed?
Yeah, just reported basically the amount of. See, let me see if there is another diagram. But no. Yes, is in according with the amount of water.
So the total amount of water, the total water in the system, and the other one is in the net.
Is the no? Is in the. This is the total amount of, is the concentration of, yes, the concentration of the water in the fluid, and this is the amount of the amount of the solid. Yes. So it's basically what we did yesterday. So trying to fix the maximum amount of CO2 possible as a fluid, and then see how much was dissolved. The same of the water. Here is just an experiment. So you have to put in your capsule that amount of water, that amount of CO2, fix the pressure, fix the temperature, and see which phases you get.
So this is something that we might do before that's then experiment to see if
yes, you
compare.
Yeah, you can compare.
So that you know what to expect.
Yeah, more or less. Yeah,
Or
exactly. So what we did, for instance, when we perform our experiments in 4D, the synchrotron, I was doing always this kind of diagram first in order to, okay, at least I expect a certain temperature conditions that I can investigate. Then you go and you test with experiments if melts is correct or not. Usually when you go to basalt, it's not so far from the reality. When you go to alkaline magmas, instead there is some problems with several phases because cyanopyroxene is quite accurate, but if you move towards leucite or amphibole, they are difficult to constrain for melts because there are not enough minerals, enough experiments to base the results. So the melts at the end is interpolating data using also previous experiments, but there are not so many experiments with these compositions. Okay, and then since yesterday we were interested in peralkaline rhyolites, pantellerites, I put also phase diagram produced at water saturated condition on the left hand side. So here we have pressure and temperature. Here is just reports the alkali feldspar liquidus. So the blue point represents where my experiments just showed that was just melt, and in the red points where alkali feldspar formed. So therefore the liquidus is more or less here. And on the right hand side, the liquidus of alkali feldspar, the blue line, and the cyanopyroxene is here. Okay, and this is my composition was like a strombolian activity in Pantelleria. If I remember correctly, it was the eruption of Cudia del Gallo. And then this instead from the Orléans group was a different pantelleritic magma from Pantelleria, was Fastuca eruption, slightly different. And you can see that there is a slight difference in the liquidus of the alkali feldspar between the two, quite similar in the cyanopyroxene. This underwater saturated condition. If you want to see the same composition, considering just different percentage of water dissolved in the melt, so before not reaching the saturation, so the saturation is reached by just here, this condition here, okay, this here. In this diagram, we have temperature, the amount of water, a fixed pressure. The pressure is 1 kilobar, so 100 megapascal. Here also they varied the amount of water, but the color gives you also how the fugacity, oxygen fugacity changes according to the amount of water that, because the oxygen fugacity is partially fixed from your experimental apparatus, okay? But then if you change the amount of water in your capsule, your system will have different oxygen fugacity. So therefore the colors represent different oxygen fugacity, okay? Going from more reduced to more oxidized conditions when the amount of water increases. Of course, increasing the amount of water, you increase the amount of oxygen fugacity. And you can see the, I don't know if you see, so this is the solidus, okay? Below here is completely crystallized. And then we have the amphibole in this case, quartz, aegirine. Of course, we form aegirine in this kind of magma, alkali feldspar, okay? Here are just two different compositions that compare two different pantellerites.
Those one, the anti-wall.
Yeah.
You would form anti-wall at constant pressure, but in second pressure, but almost also at a constant temperature.
Yeah.
Regardless, almost regardless of water.
Almost regardless of water, apparently. Yeah.
Apparently.
Yeah.
So what's the difference between the two examples?
The two I can tell you is let me see. I can tell you. Have to stop the presentation.
Because we see that for similar amount of time.
Now I can tell you exactly. Yeah. Ok, C, allora B is Pastuca Pantellerite. Instead, for comparison, the phase diagram estimated by Carlo on Pastuca Pantellerite is also shown. So the four they performed using the same composition, this and this. They have the same composition, but the range of more or less the range of oxygen fugacity is the same. I don't remember why they find this different things.
We see that already.
Yeah.
For similar H2 content.
Yeah.
We change that.
Yeah, I don't remember because I read this paper several years ago. I don't remember the reason why it's
It
different.
means that the composition of the sample controls whether
It's possible that it's not exactly the same, or maybe there is an explanation. I can send it to you. I don't remember. To this point, and I almost finished. And if you have a question, just to introduce that the effect of oxygen fugacity is important for crystallization. Will change the liquidus. We will change the mineral assemblage. So in this case, for instance, this dacite performed a QFM or nickel oxide plus 1,5. So as you can see, particularly the oxides are quite sensitive to the oxygen fugacity. You can change the temperature and pressure of the temperature of the liquidus, and maybe you can appreciate that here. This is a recent paper. These are calculation in melts using tephrite from La Palma eruption, performing simulation of two different nickel oxide plus 1,5 and QFM, so more oxidized, more reduced, and comparing the same amount of water. So this is anhydrous. This is 1 weight% of water. This 3 weight% of water. And you see how for instance, the olivine is quite sensitive. There is no. Where is the? There is no temperature. There is no. Oh, it's calculated with the temperature. Okay. So anyway, this is the temperature. Anyway, so and oxidized condition, the liquidus of olivine goes to lower temperature compared to the more reduced conditions, and then increasing water, the liquidus of plagioclase goes at lower temperature, and increasing water, hornblende will appear at more reduced conditions. So therefore, oxygen fugacity and water will affect the mineral assemblage in equilibrium.
So reduced conditions and increasing water, then we will produce hornblende at shallower.
Yeah,
Right?
exactly. So hornblende for sure needs water. If you
Reduced conditions.
and reduce conditions. So therefore, it's likely for this paper we said, okay, possibly hornblende is coming deep, close to the mantle probably, or it's forming probably one of the first phases that formed, and then during ascent you can form the others. For sure, the plagioclase seems to be the shallow phase, probably shallow in the conduit or the last part of the conduit or outside. So, and I think I finished with this, yes, with this presentation. If you have questions.
¿Tienen preguntas los que están conectados?
And is there the saturation effect? I mean, if you still continue to increase the water content, do you see like a
Increase.
drop?
If you increase, I have, I can show you. Let me take the paper. So this is the temperature, this is 5 weight%. So I'm just, you can see, all the blend appear also a more oxidized condition. Today we go to reproduce this kind of diagram. So also what you can see here is that with 3 weight% of water, so the slope of the cyanopyroxene liquidus is negative, so it's positive actually, up to the saturation. When the saturation, so around this pressure, you reach the saturation, the liquidus will change the slope. Okay, it will be like this, like the phase diagram that I showed you on the water saturation condition. So the classic slope on the water saturation condition is this one, and then it will change the slope when you go undersaturated in conditions.
So you have so much pyroxene crystallization, compression at shallow levels.
Yeah, exactly, because you go far from the limits. Because it's going.
And it's very saturated.
Yeah, exactly. Instead, if you have like this temperature, if you start from this pressure, for instance, and this temperature here, and you decrease the pressure, you decompress the system, you are going towards melting the constant temperature.
Yeah, but I mean, then just before the eruption, you can crystallize lots of.
Lots,
like
yes, because the
particles.
liquids are going towards very high temperature, yes, at ambient pressure, yes. Yeah, exactly. So exactly this way they go. No, it's this way. Yeah, you go like that. You go in that direction. Increase a lot.
Pequeña parte, ninguna, no, acá no. Hacemos un pequeño receso. Vamos a tener un pequeño receso,
Okay.
pero no va a cerrar la.
Perfecto. Hola.
Melting of the rock.
Microfono.
Microfono, sì, sì, sì.
Melting of the rock and get all the gas. Whenever the gas is going to get all the gas, you melt the rocks completely. And you separate gas from the, like when they do, for example, for noble gas isotopic analysis, where they do that, they melt the sample, the solid sample, the gas or the rock, and extract the gas.
If you do that, that can be an approach. The unique problem that is that rock experience decompression to reach to the surface. So therefore the gas, most of the water and CO2. So therefore when you do that, it's possible that the gas that you will measure is not representative of the gas at that because it was already absorbed. The risk is that for that reason, usually we use melt inclusion because they are like a capsule trapped into the crystals, and then you can use melt inclusion or fluid inclusion there. Fluid inclusion for sure can give you. Some people what they did in the past was just to take the crystal like olivine with the melt inclusion inside. The melt inclusion usually are associated with the fluid inclusion as well. So what you do is you put your olivine, your crystal, a high pressure, high temperature, and you re-homogenate the melt inclusion so that the volatile the fluid inclusion will go inside, and then you quench quickly your crystal, and then you measure that melt inclusion. And the glass basically of that melt inclusion will contain the maximum amount of volatiles that we have. So that can be an option. It's tricky to do. It's not easy, but that is one approach that it's possible to do. It's just to re-equilibrate the melt inclusion with the fluid inclusion at high pressure, high temperature. At that point, you can have a representative amount of volatiles when the organ forms. That possibly is very low in your or very high deeper depth. Well, the other approach what I can see is the people that measure gases, CO2 with the infrared and this kind of thing. They will give you total amount of CO2 emitted from that volcano. That if you do a mass balance calculation with the magma, so you can estimate more or less the percentage, and then okay, say okay, this is my maximum with percent or ppm, and then you enter in math, say okay, I'm using this just to say that this is maximum that my system can. Maths will calculate that. So it is.
So schiena lo sole, vanno cantare. Sì, chiaro.
Ah, no, la práctica del campo. Mi vecina de cuando las ciencias se encuentran en la inteligencia artificial
No vi el correo. ¿Cuándo? Qué bueno que me acuerdo que
es porque va a impartir un curso del posgrado.
Pero él hubiera, no sé.
Sí, la universidad me ha llamado. Oye,
No, a mí no me llegan esos. Es un spam también.
es el correo posgrado.igc.
Ay, por favor.
Mandaron a todos académicos, estudiantes.
Suerte. No podemos. Si quieres.
Fabio, parla español.
Hablo español muy bien. No entiendo por cosas.
You should understand.
No entiendo.
Like, I don't speak Italian, but with French and Spanish, I understand Italian.
Yeah, French as well. We have a lot of words that are similar.
Sai cosa? Si vede piccolino. Guarda.
Ah,
Anche las composiciones iniciales, quiero checar. Las composiciones van muy bien, ¿no?
no? Is it better? Okay. Okay, today we try to make a phase diagram under water saturated condition, using the same puzzle that we used yesterday. So therefore we just reopen our file that we used yesterday. And so we have to open melts. Where's my melts? Is here. Yes, no, yes.
No.
Okay. Commands, open, was this, top, so beneath it. Okay, and we have.
Yeah.
Okay. What do we need to do to make a phase diagram under water saturated condition? We have to, so the approach is, right here, this will be the basalt. So we have to consider temperature in centigrade and pressure. We are working in bar. The moment, so okay. What we need to do is to fix. Then we have to fix the water in weight percent. Okay. Okay, we have to decide which pressure we want to investigate. Now, for our case, we can do 200, 100, 50, 25, and 1 bar that is representative of the. Okay.
So what's the purpose? What are we trying to do in this exercise?
So these are the pressure. We have to, what we want to do is this at the end. Let me take this diagram here.
I want to do fixed diagram.
Yeah, we want to make a diagram like this, okay? So the philosophy is with melts, we fix one pressure, okay? And then if we want to do under water saturated condition, we have to fix the water. How do we fix the water? Like we did yesterday, I opened just to make it simpler. I open this one, just can help us to do this. I open this. Okay, you see this, you know? So if we, this doesn't reach 200, anyway. Okay, 200 megapascal means that it will be at least 48% of water. So therefore, what we do here, in our Excel file at 200 megapascal, we say, okay, just to be sure, we do 4.5 weight% of water, just to be oversaturated in our calculation. Then this, okay. And then we said 100 megapascal is here, more or less. It would be, to be sure, 3.5. 3.5, 50 megapascal. We are here. It's around 2. We put slightly more, 2.5. 25 is here, will be 1.5. And then ambient pressure will be 0. Okay. So after that we fix these, we know that if I go again here, well, it means that if we run at 25 megapascal here, okay, the pressure is fixed, the water is fixed, so it means that we are investigating the condition and the water saturated condition at fixed pressure. What we need to do in melts, we have to investigate all the range of temperature where the phases can be. So therefore, we have to start from 1300 degrees Celsius, and we run up to 1050 degrees Celsius. So we investigate every temperature. Okay, this is the philosophy. So therefore, we go to here, and we say, this is our basaltic composition. So we start from 200 megapascal. So therefore, here we have to put 450. We remove the CO2 because we are considering just water saturated conditions. Okay, here we put 450 for water. Okay.
We want to change the intensive variable.
Intensive variables. Okay. We start from temperature. From pressure, we know we start from 2000 bar. So, and 2000 bar will be fixed. Okay. The temperature, we have to go from, I would say, from 1300, okay, to 1050. Here we have to investigate every degree. Okay. So for 1300 to 1050, every degree at fixed pressure, 2000 bar.
And why?
Because then we want to know where the liquidus is. So therefore, if we do every 10, we will have an error of 10 degrees because it can be. So our phase can be, I don't know, at 1050 or at 1150 or 1160, but maybe it's in the middle. So if we take that resolution at the end, we will have that resolution with that error. If we do every degree, we are sure that maths will predict exactly where the phase will be. Okay. And then oxygen fugacity, in our case, at the moment, we can do, it was nickel oxide, yes, then we can keep nickel oxide, is okay. And then the option as well, we keep all the phases in case you have a reason to reduce your phases. In this case, we keep all of them and we see what melts will stabilize. Okay. After that, what we do, I save it.
What was the range of temperature again?
Sorry.
Stuff, I just forgot.
The range of temperature is from 1300. So 1300 I choose because I'm pretty sure that we will be above the liquidus. Everything will be liquid, I guess. And in case just the oxide can be formed higher than that, but then we see. And the final temperature will be 1050.
The buffer was the same.
Yeah. For sure, for 2000 bar and the well saturated condition, the liquidus will be shifted at lower temperature. I think we are correct. And then I'm going to save it. So that's I can go bus. Okay. And now we are ready. So we normalize and we run. In this case, since there are a lot of temperature, we will take a bit.
Because we're at 10 degrees. So
It was much faster. But when it's finished, we go to our and we go. It's out. We read it. Okay. Now, if you see at 1300, we have just liquid as was expected. Now, the philosophy is we have to find the first appearance of each phase. Okay. So to do so, usually, since here is every degree, it takes a lot to find. Why do I just do the finder and I do Clino, for instance. Okay, and you see that the Clino. So in my case appears at 1056.
what is it?
Is the Clino. The first Clino appear at 1056.
How can you open?
You open?
What's it called? Yeah, because I cannot see it. Visualize the final. looking for it.
In your corner?
Also, I can find also, maybe the name has changed, that's with S, what's that?
Max out. Sì.
Okay.
I don't know.
Command F. If
Okay.
you do Command F in your Mac or Control F in your Windows, you
Okay.
will have the finder, and you write. So Command F to open the finder, or Control F, and so 1056. So it means that what we need to do is this. Sorry, I swap with this, and I'll explain why. Put the water here, put the pressure here, put the temperature here. I put several temperature. We see how many phases. I put the cleaner here, the olivine, and the plagioclase. Okay. So we do like this. So this one, this is 1056.
Fabio, you use 2000 bar.
No, 2000. Sorry, sorry. I wrote in megapascal. 2000, 1000, 500, 150, and 10. No, and 1 bar. Yes, 1 bar is correct. So this 1056 represent the liquidus of our phase, for in this case for the clinopyroxene. So what we do then, clinopyroxene is quite low. We see the olivine, and the olivine will appear at 1086, 1085, 1085.
Ah, la prima volta che appare.
Yeah, no, that is the liquidus.
Yeah,
No?
ok.
That is the liquidus. But then you can find olivine.
Esatto.
That c'è sempre. Okay, you see at the first time that it appears, the amount of, just to explain. So basically, 1085, this is the condition that we run our, then we have the liquid will be, this temperature will be 95.78 grams. And then we have 95, yes, 95. Then we have 0.20 olivine, just the first appearance, and 4.30 grams of spinel. So, and here are summarized the total solids, okay, and the density. And here the viscosity of the system considering the crystals, so the crystal fraction, okay. And so what does it mean? That these grams can be, since they close nearly at 100, as you can see the system, there is a big error anyway, then 100.34 doesn't make any sense, it's 100. So the amount of olivine is less than 1% in volume fraction. If you, okay, and the spinel is more or less 4%. For volume percent, for volume 4%. Okay, that is the meaning of this. Okay, so therefore, this when you, if you want to check the crystal fraction of your rock And the simulation, you can do it because you can actually quantify the amount. Yeah. Yeah.
So what was the temperature?
1085. Okay.
Do you want to make 1080? Busca la primera vez que te aparece, es primer archivo. Tienes que ver la temperatura a la cual por primera vez ves.
Sí, pero como que buscándole con el.
No, pero te salen muchos. Te vuelve a salir donde estabas. Busca donde viene la temperatura. 1085. ¿Te funciona, no?
Sí, pero no parece. O sea, me sigue siendo cero.
¿Subiste?
When you say the first occurrence of olivine temperature, it's like the minimum temperature of which olivine
Is the maximum temperature.
maximum.
Yeah, because above you can see olivine will disappear. There is just spinel. Okay, the 1096 doesn't exist anymore. So, and if you go down, the amount of olivine will increase. If you go down, it will increase.
Okay, so it's a minimum mass fraction.
Sí, claro. De la,
Yeah, it's just the liquidus, because if you remember the liquidus that we discussed before, as soon as you touch the liquidus, that crystal will be formed, okay, and there will be, if you remember the ratio in that plagioclase diagram was 99% melt, 1% crystal. If you decrease the temperature, the amount of crystal will increase, the amount of liquid will decrease. In fact, if we go down in temperature, I don't know, we reach the minimum that we put. So 1051, so you see that the amount of liquid passed from how much was before 95 something, and now we are nearly 90, and the amount of olivine increased to 2.39.
Okay, so it's the higher temperature and mass fraction.
Yeah. So what we observe that at 1050 we don't see plagioclase, for instance. We can put olivine, we can put spinel. We see spinel where. So probably plagioclase is a lower temperature. Now we have to investigate where. So we do spinel. Spinel is oh, didn't take me. It didn't take me the. Oh.
Thanks to 1 degree increments.
Uh, 1131. 1131. Allora we had also spinel here. So 1131. Okay. It's clear that the liquidus of the bulk is the oxide. Oxide is the liquidus of the bulk. Is the phase at the higher temperature. Now we miss plagioclase because basically we investigate a range of temperature where plagioclase is not present. So therefore, what we do, we can run again this, and we decrease the minimum temperature to, I don't know, 1020, for instance. Okay, so we close this. No, we keep this, it's okay. We just rerun this condition by changing the minimum temperature to investigate where the plagioclase is, because we choose a range that is not It's good for the others, but not for the plagiotes. We cannot stabilize the plagiotes. Yes. Okay. And we run again this one. Yes. Yes. Open. That's, what's the name? Bus. Yeah, we have an intensive variable. Instead of 1050, we put 1020. It should appear after that, I guess. 1020 as a minimum temperature. Apparently, there is no plagiotes. It doesn't stabilize plagiotes as well. So it means that plagioclase is not stable at that conditions. Okay, that's weird. Doesn't have plagioclase. Okay. We keep going. So since we cannot stabilize plagioclase at this pressure, we keep going to the other pressure that is 1000 bar, okay, at 3.5% of water. So therefore we run these. Yes, yes. Sì, esatto. Questo. So at this point here, for the water, we put 350. And intensive variable, we put 1000. And we keep the range of pressure and temperature the same. So it should be okay. And we do normalization, right? Come on. Another lower pressure. So, okay. This point, all we do is Control F. Olivine apparently, of course, the Spinella is the best one. Spinella is 1122. Allora, 1122. Then Olivine 1102. 1102, 1102. Then the other one we can put on a pyroxene. Cleaner. It's at 1064. 1064. And 64. And then yeah, we can introduce feldspar. Okay. Okay, and we have the liquidus at 1000. Now we move at 500 bar. So everything. So everything. Again. Yes. Bus. Okay, for 500, the water is 2.5 should be okay. 2.5 should be okay. We decrease the pressure at 500. Normalize. And we do the same. Control F. Spinel. Now the olivine is higher temperature. 11, 12. Spinel. 11, 12. Olivine is 10. Temperature. Olivine. It's 1122. 1122. Lino. Also the Vespa now is higher. The Vespa is at 1087. 1087. And the Clino 1086. Okay. Okay. We close and we run again at 250. $150 is 1.5. It's a variable we write 50 to 50. Yes. Quindi 11,36. Spinella. Upload. It's 1108. 108. Then it's 1111. No, that's right. And then the cleanup. Then okay. Are you here? The thing. Okay. Last one. Anhydrous at 1 bar, so ambient pressure. We do. Yes, not this. We open this. Desktop M bus. A questo punto I remove the water completely. Anhydrous, for pressure I put just 1 bar. 1 bar. Okay. Anhydrous, completely anhydrous. The last. It's for 1180. And 76. 76. Clean. 1147. 1147. And the spinner. Yeah, 31. Okay. Yeah, this now what we do is just to make a diagram. And insert this one. What is doing? Yeah. It's weird. Okay. Select it. So this is like the angio phase. X è la temperatura. Y. This. But this. The pressure. This. And then 5%. This. Okay. In the end, we should have this. We have a diagram like that. When the orange is the plagioclase, the yellow is the cyanopyroxene, the gray is the olivine, and this is the oxide. So the plagioclase is this one, and the pyroxene, olivine, and oxide. So basically, we produce a phase diagram where it means that here is completely liquid, is basalt. Then at this condition here, there will be just oxide. If we go lower, there will be olivine and then pyroxene. Apparently, plagioclase appeared from 100 megapascal, or maybe we didn't investigate the right temperature. 200 megapascal, it's even lower than 1000, I don't know. Seems weird. No? And is the slope of the plagioclase that will go to be the phase at higher temperature and ambient pressure will cross with the pyroxene, as I said before. The pyroxene is here. Go to remain at lower temperature. So this is the phase diagram of this basalt and nickel oxide under the secondary conditions. You do your bar composition with your rock, as you will get where the phases are.
So you then can compare this diagram with what you see in the thin section.
Yeah, exactly. So you say that if you have a plagioclase and pyroxene, for instance, and or if you have, in this case, if you have just olivine in your basalt, it means that and probably the condition were here in this didn't cross the pyroxene or the plagioclase if they are present in your basalt for two reasons, or because the system was at equilibrium at these conditions, so therefore no possibility for pyroxene and plagioclase to form, or if they cross this condition and they were here, it means that the magma was at this condition quite quickly, where it's showing just equilibrium. So therefore there is like a stagnation here, and then cross this condition fast towards the surface, and these two phases were not activated because this phase diagram is at equilibrium condition. But then this equilibrium can change completely the story. So you cannot, this equilibrium can inhibit some phases because the kinetics is not so fast to react to pressure and temperature changes. So if it's too fast, maybe it doesn't mean that your rock, your magma didn't pass through this condition, but that passed through too fast.
You didn't have time to kill it.
Exactly. Instead, if you find all the phases, plagioclase, pyroxene, oxide, and olivine, so it can be a condition for sure lower than you see the plagioclase is here. So if you think that based on what we said yesterday, if you fix a range of pressure with your volatiles, so for instance, you fix a range of pressure that it goes between 100 and 50 megapascal. So your system is here. And then through this, you can fix the temperature, because if you have all the phases, it's possible that the temperature is below 1050 or here what we have 1080. So therefore, the range of pressure will be between 50 and 100 megapascal, and the range of temperature will be between 1050 and 1080 for your for the formation, or below than that. So then depends the other information how below in temperature can be. So can be at 1000 your system. It depends the grade of the degree of crystallization. If your rock is completely crystallized, for sure you are far away from these liquids. If you have a 10-20% of crystallization, you will be closer to your liquids. So therefore, then you have to cross all the information to constrain your pre-erratic conditions. We can see this part about the distance from the liquidus and the effects tomorrow. I made a lesson dedicated to this in order to say, okay, how far from the liquidus the system is if you fix the pressure, basically. Yesterday, with the technique that we introduced yesterday, we can fix in some way the pressure or the range of pressure. In this way, we can start to range to fix to constrain the pressure and temperature based on our crystal mineral assemblage. Then to narrow down your temperature to say, okay, now more or less I'm here with the less error. You need other information that we produce.
This is the complete state of the CPX. So we have the CPX on the out.
Starts. No, it's correct. It's different for us.
Yeah. Maybe this is patch. CPX doesn't out.
No, it's the plugin place. I think you added the value to the plugin.
Yeah, okay.
Then melts also gives you, if you see, another information that is important is that the alkali feldspar, for instance, an ambient pressure, we do the example of the feldspar. We go up and we find the feldspar, where the feldspar is. Okay, the feldspar at close to the liquidus, the anortite number will be 73 more or less, 72.8. Okay, and now the temperature we are 1180 degrees Celsius. We decrease a little bit, like we go to 1150 just to make an example. 1150. Okay, so the anortite number, as we discussed today, goes to 67. Okay, so exactly what we said today. So decreasing the temperature, the liquids will evolve, and so the anortite number will decrease, and you will be more orbitic. Okay, so at equilibrium condition, this will be the equilibrium for that plagioclase. You don't see any zonation at equilibrium condition. It doesn't mean that your system will work at equilibrium condition, but that is the result. So the 4 means that if you have a plagioclase with if you calculate the anortite number, of your plagioclase. That is another information that give you where you are in terms of temperature, if you are far away or closer to the liquids, together with the fraction. Because you will see, of course, going far away from your liquids, you will increase the undercooling, and therefore you will increase the crystal fraction. We'll see tomorrow.
So only the plagioclase you see on the section is like homogeneous.
If you don't have zonation, you have just one anorthodic number, so it means that possibly was formed in one specific condition. And I think random melts, particularly with basaltic andesite, you can be quite precise in terms of temperature. If you go towards dacite, rhyolite melts is a little bit less precise, but the error can be 30, 40 degrees, maybe 50 max. That is not trivial, is not. But for melts, for the current version of melts is, I think, it's the best that we can. Yeah.
Then also you have this found plagioclase, you can get microprobes of each zone, you can also assess conditions of the evolution.
You can do it. Yeah, you can. And for sure, if you have a trend, normal trend of zonation or a continuous zonation, like you can see here with temperature, you can track like a cooling condition or magma cooling. So moving, so that was recorded by the plagioclase moving from high anorthodic number to low anorthodic number. If you have a more complex situation like oscillatory zone, that you have to invoke other processes, you have to, Question so far is clear the philosophy is how to construct this.
It's more about the strategy. So you go to the field, you get some pathways, some andesites, measure the local composition.
Yeah.
You use this local composition to decide the model.
Exactly.
But how do you fix again the correct weight percent of H2O?
Yeah, you have to.
So how do you fix the first variable?
So if you want to just
Caracha.
Sí, se cayó aquí en la vieja, se quedó de la espalda. Se cayó de aquí, de arriba.
It's like one German.
is it cricket?
No, German cockroach.
Perdón.
No.
So you get the sample, you measure the major oxides conditions,
Yes,
and
and
then how do you fix the
then
first variable?
if you want to just to calculate the water, you can use the same approach that we said we did yesterday. You will know the saturation for each pressure. You don't need to measure water in your sample, so you can measure after. First of all, you can fix the saturation. So this diagram here, this you can calculate.
How do you so it's based on the mineralogical assemblage that you.
No, well,
You set the condition if it's saturated or undersaturated.
Okay, if you want to, okay. So what you can do, what we can do now or tomorrow, it depends how you feel. Our first approach was, okay, we have our composition. We assume that everything is saturated in water, okay? Based on this, you have to calculate this, but also this, you can calculate with your bulk composition. You don't need anything else. You need your bulk composition, you use the Moore model or the MELS, and you calculate the maximum amount of water for each pressure, okay? You calculate your saturation. At that point, you run the phase diagram.
So first we need to calculate the saturation.
This one, because yeah, because we fixed. You remember we fixed.
This is what we did yesterday. See,
Exactly. We
So,
fix the for each pressure we fix a certain amount of water just to be sure that we are saturated. So in order to get this diagram is valid just for water saturated condition. Okay, this is the more simple approach. So then if you want to make it complex and say, okay, since I don't know, because you have not measured the water in your sample, because maybe it takes more time, you have to go to FTIR or Raman or so on. So what you do, you want to change the water like the diagrams of the pantellerites that I showed you before. So therefore you assume 0, you assume 1, 2, 3, 4. So you assume all the values below your saturation, okay? And then you basically, at that point, you fix the water and you change the pressure, okay? And you change the pressure. If you want, we can do now. We can do tomorrow as you feel if you feel tired. So, and we see with the same composition how the liquidus will shift under saturation, basically of water. So they will shift, and so therefore you construct several scenarios: the saturation, and then different. The different basically water content under water saturated conditions. So water under saturated conditions.
Okay.
So you don't reach the saturation, but this means that you have a range of water that you have to cover, because at 200 megapascal you can have if the saturation is 4.5, you have 4, you have 3, you have 2, you have 1, you have 0. Okay, and you have to make the diagram for all of them in order to cover each scenario. You will end up with several diagrams. With the first one is the saturation. The rest is water under saturated condition at 3, 2, 1, 0 if you want. If you think that your system is a complete analysis, it's unlikely, but it can be. And so therefore you will have a picture of your composition at different conditions, and you see where the liquidus are. At that point, what you want to do is to measure water and CO2 in order to constrain that pressure and temperature. At that point, you have a clear picture of your magma in front of you, where the things will occur, so where crystallization will occur. And at that point, you will constrain your system. At that point you will know where the phases will be formed, at which water condition, at which CO2, or which pressure, and whatever. So and you will constrain pressure and temperature. You want, we can just start from, so continue with this composition, and we calculate, I don't know, we assume 1 weight% of water, and then we recalculate this liquidus 1 weight% of water in the same range of pressure that we, and we see where the liquidus will be after. So therefore, what we do is we just copy this. Let's copy the same things. Another. This point will be 1 weight% 1, 1, 1, 1. Yeah. And change all of this. So this. Se lasciamo uguale.
So in this case, this will be undersaturated.
Undersaturated, exactly.
Lucrative.
For most of the condition.
Almost.
Of course, yes, 1 bar, of course, it will not, it will be 0 anyway. So
Yeah.
we have no chance to have. But then at 250, for instance, at 250, the saturation was 1.5. Yes, will be undersaturated also at 250, possibly. Yeah. Yeah. And we see what we get. So 250 will be close to the saturation. Okay, and we can start from, so we close everything again. So here. And then we throw away this. Yes. That's at this point here in the water we fix 100 and we are happy like this for all our simulations. Intensive variables. Now that we decrease the temperature, means that the liquids will shift to higher temperature. Just to see the plagioclase, we do 1000 right here, just to be sure that it will appear. And what we can do, we can run also at 13. No, at 1300 will be okay. Will be okay. Otherwise, the temperature I left 1300, but I went, yeah,
Down
to 1000, just to be sure that I'll see the plagioclase this time. At the top. 2000. Okay. Okay, Control F. Cosa spinella? Il primo no, spinella non è il primo, ma direi change completely. 1121 spinella. 1121 spinella. At this point it changed completely. So for the primo, this one is. We have to try. Olivin 1120. No. Olivin. Oh, where is the first one? 1161. Sì.
We are CO2 change.
CO2? No, we are working just with water.
But we are CO2.
Yes.
Parameter change.
I think so, yes, because then it will calculate the equilibrium between water and CO2. And then, yes, the liquids will shift a little bit. It's possible that if you add CO2, the liquids will go up a little bit.
Yeah, it's not a great change, just.
No, it depends, no, it can be small change.
Okay.
That will be 1135. 1135. and then Clino. Yeah, 45. Okay. And this is the first. Okay. Go to run at the same amount of water, but 100. So 1,000 bar. Then oops. Scroll down.
Scarafaggio, mazza. The temperature, so far. Yeah, okay. But the range of ocean and temperature should be fine. Put also 100, I think. What I'm going to increase just to be sure is the temperature, the starting temperature at 1350, and the minimum temperature 1100 is below than that. We don't go. And that's it. Mi ammazza la vergine.
E voy a abrir la puerta. Sale. Listo. Quanto io c'è? Io sto chiedendo di stare.
So,
I don't know if it works for you, but I've tried not to close all the windows, just to change the balance and execute, and it works.
What?
So that I don't know if it depends on the version or the computer, I have to close it, or maybe it doesn't matter. I mean, once you run I execute the experiment.
Yeah.
With the same window, I change again the parameters, because I'm not changing again the
Okay.
composition, just change pressure, change the.
And it works for you?
And it works when I execute it
Okay.
again.
I'll try later. We'll see.
Without erasing. So try once you finish to execute it. Because we don't change the major element composition, just change again the pressure. And then execute.
That's good.
I don't know.
23.
Okay. I don't know. No?
So therefore you don't. So therefore you change just the pressure. No, for me it doesn't work. It doesn't calculate. I don't know why. Maybe it's the version. Maybe it's the version. You have to restart again. Doesn't work for me. At least in my version. Okay. Mm, 48. 48.
Dai, che schifo! Ma ammazzala! Mi fa troppo schifo! Non riesco. Ah. Ma dai.
Yo pensé que era para ver.
No, sería menos.
Ah, sì. Non so da scrivere.
Si lo vuole, anche io, se era lo vuole.
And 27. Okay. I'm going to run the last ambient pressure. The ambient pressure with so the ambient pressure actually we have because it's the same temperature that we got before. Doesn't change anything. So okay, like this. So therefore, I'm going to plot. So,
Non l'avevo ora e credevo che era adesso.
okay. So we have this. The is okay. This is the diagram. Yes. La pendenza, sì, perché when you are undersaturated, the liquids will shift, and the slope will shift, and then it will be like before with this gap here, just when you reach the saturation. So at 1 weight% of water, more or less 20 megapascal is the saturation, and the liquids will change the slope. Of course, as you can see, your phase equilibrium changes
change dramatically if you consider water saturate condition or so basically here the cyanopyroxene at 200 megapascal was stable below 1050 more or less. Now if you take the cyanopyroxene, now is the gray one? No, is there a yellow one? It's 200 megapascal is stable below 1140. So there is a big difference, 100-degree difference. Using water or the liquid switch at the temperature.
O sea, se mantuvo diseño. Bueno, deberían darlo.
get it. No, we can copy this. You put all together. This will be the difference. Yeah.
Sí, sí. Disculpe, tengo que terminar la sesión. Nos vemos. Ya solamente sé que me pasa claro.
It's just a copy all the liquids together. This are the saturated one, and then we shift completely.
C'è bisogno inizia a start to crystallize at high temperature.
Exactly. So exactly well, just to link what I presented yesterday in terms of remember when we discussed about the effect of water on the liquidus. This one, no? Saturated and then dry. These are the two extremes. But in the middle, I said there are then all intermediate situation where you can have 1% of water. So basically, the liquidus, particularly of the plagioclase, will shift like this. We change and then will be closer to the dry one, decreasing water. Increasing water will be closer to the saturated. That's just a theory, yeah? But then you can see in your diagram that you reproduce basically. Of course, as Lucia said, this will change the initial temperature where the crystal will be formed, and so it can change dramatically in geology if you are a low temperature, high temperature. Change completely crystal fraction, magma and viscosity. Yeah.
So if you have your sample and try to define the pressure and temperature from the conclusion, and you plot. And then you see that your sample, you don't have the same crystal phases that accordingly. So it's right.
The reason this can be that antichrists,
Yes.
so something that was inherited. This you can see through this, or if you calculate, for instance, if you do the chemical equilibrium, Juriquilla thermometers, or depend on you can see if they are in equilibrium or not. And so, and combining this with that, you will have a clear picture if your crystals are formed from the now they were inherited during acids. It would be kind of minerals, and they are there, but they were not formed. Yeah. Questions?
Water exercise.
Okay.
Today,
See,
I think
Now you are entering in the sea. Okay. So yeah, you can do. Tomorrow we had some complex, maybe we can run some, or we can run the same things with different composition, or we can try to do some fractional crystallization in maths, because it's also possible to do it.
Yeah.
I have no use too much, but there is an option, basically, you can fractionate the solid, or you can fractionate the liquids, and then you see what the results are. We can try to do this. And then maybe Thursday, maybe we repeat the volatiles.
Yeah.
And, so now we start to connect everything together. And from tomorrow, maybe you will the lesson from I'll add how crystallization works more in detail. So therefore you will better understand what it means far or close to the liquidus with your textures. So when you look at the textures, then you will connect immediately textures with these diagrams, and you will understand where you are.
Yeah.
Okay.
Bravo, nice. Citlali, ¿todo bien? Platícanos.
Sí, ahorita estaba comparando mis resultados, pero sí, todo bien.
Escuchamos. Suele, a ver.
So, I close the mic.
Sí, todo bien, doctora, gracias. Nada más estaba comparando mis resultados, pero sí, todo bien.
Habla ahorita.
¿Ya me escucha, doctora?
Sí, ya. ¿Cómo estás?
Muy bien, doctora. Ahorita nada más estaba comparando mis resultados, pero pues sí, todo bien. Ya le agarré la onda con el programa.
Perfecto.
Sí.
Un capítulo de la tesis.
Un capítulo. ¿Tienes las
Sí.
composiciones químicas de tus pomes?
Tiene todo.
De hecho, de eso estaba pensando de nada más que la anexe y toda esta información.
No, termina con lo que tienes.
Ok, sí, está bien, mejor.
Bravo. Muy bien, listo, súper. ¿Tú imprimiste tus secciones? O vemos aquí las tienes.
Sí.
Va, ¿tienen hambre o quieren verlo después o ahorita? Tú depende.
Oye.
¿Hay hambre?
Sì.
No te vayas a cenar.
Ok.
Nos vemos a ratito.
Ok.
Como ayer.
Sí, como ayer.
Va.
Temporada, sì, esatto.
Sí, No, domani vi invito a cena a casa. Mañana vienen a cenar a mi casa.
Ahí vas.
Después de su seminario,
Ajá. Lo puedo.
vamos a mi casa. Andiamo a casa mia a mangiare. Sì?
Ya, yo he detto Fabio che possiamo andare.
Certo. Sì, sì.
Ritorno ieri,
Sì.
ritorno a Lucia.
Sì, vedo qua vicino.
Very well.
Ajá. Sí, no, chao. Bueno, nos vemos, Citlali. Lástima, te vas a perder la cena.
Hasta mañana.